Hello everyone, I hope you are all fine and doing well. Uh, Last session we started talking about some example problems and how to find the reactions in a beam, and also we tried to see whether a beam or a structure is stable and determinate or indeterminate. Today we are going to continue solving more examples, and before starting this, I want to say that if you have any question about the previous examples or about the previous discussions that we had over the presentation files, don't hesitate to send me your questions. I can answer them over email, or if necessary, we can have WebEx call to make sure your questions are answered. Before starting the new example, I wanted to do a quick review on finding the force components in the major vertical and horizontal directions. And it's usually done in two ways. Let's say this is the force that we have in a problem, and it is located at an angle theta with respect to the horizontal axis. A very common situation that we might have for forces in engineering problems. If I want to find the horizontal component and vertical component of this inclined force, I can simply multiply the force by cosine of theta to find the horizontal component, or fx, and I can simply multiply the force by sine of this angle theta to find the vertical component. This kind of rule is useful when we have the angle between the force and also the major axis, major x and y axis. But in some situations, instead of having this angle, we might have the size of the sides in the triangle. Like for example, we might have A, B, and C as the dimension of the triangle, these triangle sides. In such situations, we can directly calculate the ratio of these sides with respect to C, and then use it as the equation for finding these components. So over here, I could say the x or fx is f multiplied by cosine of theta. Over here, I can say fx is equal to the force multiplied by the horizontal side over c. And for vertical component, I can say force multiplied by the vertical side over c. All right. After the quick review of finding the force components, now let's take a look at this example that I have as example 4 in the list of examples and see how we can find the reactions in this kind of frame over here. As you all know, the first step in finding the reactions and in general in structural analysis is to find the free body diagram, meaning we have to look at the supports and put the corresponding forces for each support that we have in the structure. This is my structure. Let's see how we can put the forces instead of the supports. Over here on the left side, I have a roller support. Over here on the right side, I have a hinge support, right? How should I put the reactions? Based on the definitions that we had in the presentation file, we know that for a roller support, it's only one reaction, just one force perpendicular to the plane or to the level that the roller is located in this direction, vertical direction. And for a hinge support, we know that it's going to be two reactions, one in the vertical direction and one in the horizontal direction. Over here you can see I have added the reactions. This is the two reactions at the hinge support. This is the one reaction at the roller support. So if I show it like this. So as you can see now, we can compare the reactions versus the supports. The other thing that I'm going to add to the figure are these additional information about the incline force that we have over here. I know that the forces that I'm going to write are based on horizontal forces and vertical forces. So I need to be able to find the horizontal component and vertical component of this distributed load over here. This is similar to the case of the last example. We had a trapezoid shape for a distributed load, and instead of considering the whole trapezoid, I divided the force or the distributed load into two shapes. One rectangular shape, as you can see below the red line, and one triangular shape on the upper level of the red line. This way, it kind of makes the situation easier in terms of finding the force and the centroid of the force in these distributed loads. As you may remember, I called this approach superposition because we are superimposing the influence of these separated distributed loads on each other to find the result of this total trapezoid shape distributed load. Finding the components of these inclined forces are not difficult, as I talked about earlier. If we have a force in this direction, which is this case over here, the horizontal component is the ratio of horizontal side over this inclined side, and the vertical component is the ratio of this vertical side over the inclined side. In this specific case, we know the size or the dimension of this part of the frame, which is the square root of 24 squared plus 10 squared, right? That will be 26. And I can simply calculate the ratio of 12 over 26 to find the horizontal side, or 10 over 26 to vertical side. Over here I have the simplified situation. We know that the forces are directed in this direction. The horizontal side will be 10, or I just calculated the ratios. 10 over 26 is equal to 5 over 13, and also the vertical side is 12. So this is direction of the force. If I want to find the horizontal component, that will be 5 over 13. If I want to find the vertical component, that will be 12 over 13. Right? I hope it clears the approach and it helps you to kind of follow the approach for finding the force components. But if it doesn't, let me know. We can have more discussions about finding force components in different problems. But I just tried to quickly review this because I believe we had this in the statics at first. So I didn't spend much time on finding the force components, but if it is necessary, let me know. We can have more discussions about finding the force components. So let's go to the second step and see if the structure is determinate or not. We know that the equation that we need to solve is this equation. R is the number of reactions. We had 1 over here, 2 at point C, 1 at point A. So these are the reactions. Summation of these is 3. So R is equal to 3. And then EC, we said, is the equations of condition. If we have a hinge in the middle of or inside the structure, EC will be 1 for that specific hinge. And if we have a roller inside the structure, EC will be 2 for that roller. For this specific problem that we are looking at. We don't have any hinge or roller support inside the structure, so EC is equal to 0. Putting these values in this equation, I is equal to 0, which means that the structure is stable and determined. The next step will be using the equations of equilibrium, right? As you can see, I have the first equation which says summation of forces in x direction is equal to 0, and I have to just look at this. Let me bring it to the view. I have to just look at this building, look at this frame, and calculate the summation of forces in x direction. We have this distributed load over here, which we considered as two separated loads, one the rectangular shape and one the triangular shape on the top, right? So for the rectangular shape, I know the total force because of the distributed load will be area under the load. That will be 2 multiplied by 26, as you can see over here. And then I have to find the horizontal component of this inclined load. That will be 5 over 13, right? So 2 multiplied by 26 will be the amount of force, and then multiplied by 5 over 13, that gives us the horizontal component. This triangle over here, I hope it helps you understand the meaning of horizontal and vertical component with respect to the direction of the force. This red arrow is in the same direction as the force that we have over here, and based on this we can define the horizontal and vertical directions. So I could find the horizontal component of the rectangular load, and now I'm going to calculate it for the triangular distributed load at the top. The amount of force because of this distributed load in triangular shape is the area under the triangle, which will be this side, and that side is equal to 3 minus 2, so 1 multiplied by the length, which is 26, divided by 2. That is area of triangle, calculated over here. And then I have to find the horizontal direction of this load, which is the same idea. Multiply it by 5 over 13. Right? So that gives us the horizontal component of this distributed load over here. And then I have to look at the rest of the structure and see if I have any other horizontal force or not. I don't have anything over here, but at this support at point C, I have Cx. So I'm going to include it in the equation over here. Alright, so this is the equation, and as you can see, the only unknown in this equation is Cx. So I can simply use this equation to find the value of Cx. Calculating these values, Cx will be minus 25 kips. I'm getting a negative value as the answer for Cx, or as the solution for Cx, which means that the actual direction of Cx is in opposite to what I assumed for point C. So at first I assumed Cx in the right direction, and then when I calculated the value that I got is negative, which means that my assumption is wrong and it is in the other direction. You don't need to modify the forces that you put in your free body diagram. All you need to do is to consider this negative value in your further calculations. But make sure also you put the note in front of the forces that you calculate to make sure you understand the direction of the force. So I got this as a negative value, which means that the direction is to the left. Let's write the equation for summation of forces in the y direction. As you can see, this is mentioned as equation 2 over here. summation of forces in the y direction is equal to 0, and I always assume positive in vertical direction is of y. So let me go back and look at the problem to talk about the forces in the vertical direction. The first force is reaction at point y, at point A, right? So AY is the first force in the vertical direction. Then I have two forces because of these two distributed loads. For the rectangular shape, the vertical load will be 2 multiplied by 26, that is the total load, and now the vertical component will be 12 by 13, right? So 2 multiplied by 26 multiplied by 12 by 13. And then I have the triangular shape. For that, the amount of load will be 1, which is this side over here, that is 3 minus 2. 1 multiplied by 26 divided by 2, that will be the total amount of load. And since I'm looking for the vertical direction, I have to multiply by 12 by 13. Let's take a look at the equation quickly and see if we have these values in the equation. So AY, as I said earlier, the vertical at point A, and it is positive because the force was upward. These two values are the forces because of this one is the rectangular load and this one is the triangular load. Pay attention to the negative value or the minus in these locations because we have a downward component of these forces, so the sign should be negative. I have 50 kips over here, so minus 50, and I have Cy at the end, which is plus Cy at the end of the equation. As you can see, these values are mentioned in this equation over here. So in this equation, I have two unknowns, Ay and Cy, and thus this equation alone is not going to help me in finding these two unknowns. But if I write one more equation, I will have two equations and two unknowns, which means that I should be able to find the unknown values. For the third equation, we know that we have to find the summation of moments about a point in the structure and set it to 0. I'm going to say summation of moments about A, point A, is equal to 0. And for that equation, I need to just find the moment because of each of these forces about point A. This is calculated over here. But let's go back and take a look at the problem or the configuration of the frame and see how should I find the moments about point A. So this is point A, and I want to find the moment of all the forces that I have in this structure about point A. The vertical reaction at A is located at A, so it does not create any moment. Then I have this rectangular distributed load. The moment because of this load will be the total force multiplied by the distance from centroid of the centroid of the rectangle to the point. So that will be 2 multiplied by 26. That is the total force, and then the center will be 13, right? The center of this rectangular shape is 13, and that will be the distance from centroid of the shape to point A. As you can see, the total length is 26. Dividing it by 2 gives us 13. So that will be the distance from centroid of the rectangle to point A. So 2 multiplied by 26 by 13 as the distance from centroid of the rectangle to point A. The other thing that we have to make sure we include in our calculations is the positive or negative signs. As you can see, I always assume positive sign or positive direction for moments is counterclockwise. So whenever a moment is in the counterclockwise direction, it is positive. If it is in the clockwise direction, it is negative. Over here, you can see the moment that this force creates about point A is clockwise, right? It is in this direction, right? In this direction. And thus, we can say this value is clockwise and negative. As you can see, I have it over here. 2 multiplied by 26 multiplied by 26 over 2. This is the moment because of that rectangular shape in the distributed load. And this is negative. The same idea can be applied for the triangular shape. Just finding the amount of load is over here, area of the triangle, and this over here, 26 over 3, is the distance from centroid of the triangle to point A. Let me show it to you over here. So this is the triangle, right? I know that center of the triangle is located at 1/3 from this side over here, or 2/3 from this point over here. So the load will be at this point over here at centroid of the triangle. And the distance from centroid to point A will be 26 divided by 3. As you can see, that is calculated over here. So those are the two moments because of the distributed loads. I have also one moment because of this 50 kips load, and the direction of that is also clockwise. So the moment will be 50 multiplied by 36, and of course negative because the direction is clockwise. Then I have Cy, which is causing a moment counterclockwise, which means the sign should be positive. So Cy multiplied by 48, and that is the other value that we have to calculate in our calculation. We could calculate the moment because of this reaction at point C. As you can see, Cy is located at point C and the direction is upward in the free body diagram that we draw over here at first. So the moment because of this will be positive because the direction will be counterclockwise, and the moment will be Cy multiplied by the distance, which is 24 plus 12 plus 12, which will be 48, right? That will be the moment because of Cy. There is also one more moment that I have to include, and that moment is because of this horizontal reaction at point C or Cx. As you can see, the moment that it creates about point A will be clockwise, so that should be negative. And also, I have to include the value that we calculated for Cx over here, which is minus 25. Right? So that is calculated over here. This is the last term plus Cy multiplied by 48, and then this is the moment because of Cx. Please make sure you include or kind of understand the meaning of these two signs. The first minus is because I assume the Cx is in this direction, and then the moment that it creates based on this free body diagram is in the clockwise direction, right? But when I calculated the Cx, I found it as a negative value, which means that the actual direction is to the left. You can do two things at this point. You can modify your free body diagram based on the result that you found over here, or you can keep it as it is and solve all the equations and the rest of the problem based on this direction. But whenever you want to put the value of Cx, put the negative value. And this is what I did in my calculations. I didn't change my free body diagram. I just include this negative value that I got in my equation in the calculations, and this is the approach that I'm going to follow in the rest of the examples. At first, I assumed a free body diagram, and then I'm not going to change my free body diagram, but I'm going to include the positive or negative sign that I got in my calculations as the value for that force. So based on this free body diagram, Cx is creating a clockwise moment. So that is the negative over here, minus, and then I have to multiply the force by the distance. The force itself is minus 25 kips. This is the force, and the distance is just 10 feet. Distance from the force to the point where we are calculating the moment about. That is over here. So vertical reaction at point C will be 48.72 kip upward. Based on this equation, summation of moments, you can see that the only unknown was Cy, and I could simply calculate it. And since I got a positive value, it means that the direction of Cy that I assumed as upward in the vertical direction is right, and the force is really upward. I mentioned it in the parenthesis over here, and I can go back and use this equation as summation of forces in y direction equal to 0 to find the other reaction, or AY. Cy is found over here, so I can return it to equation 2, to this equation, as you can see, equation 2, and by returning the reaction, vertical reaction at point C to this equation, we can simply find the reaction at point A. See, this is the reaction that I could find earlier. I'm going to return it to the equation of summation of forces in vertical direction equal to 0 to find the reaction over here. This is the equation that I'm talking about. This is the equation. I could find Cy in equation number 3, and now I'm going to return it to equation number 2 to find reaction at point A. This is what I did over here. As you can see, I said equation 2, just meaning I am returning to equation 2. Ay is the unknown value. I just put the value of Cy, as you can see over here. And now by solving this equation, we can simply find the value of reaction at point A as 61.20 kips, and that is upward, right? I have also one extra step, which is just trying to see if calculations are right or not, and that is writing another equation and checking if the values can solve the equation properly or correctly or not. In this case, I'm going to calculate the moments about point B. The moments about point B. Summation of moments about point B. It's just a point in the structure. We know that equations of equilibrium should work in all the points and regions in the structure. So summation of moments about point B is equal to 0. I did put all the forces that I calculated in the earlier equations for this equation. Summation of moments about point P is equal to 0. And then if I could get 0 at the end of the equation, it means that my calculations are correct. And if not, it means that I have to go back and modify my calculations and see what's wrong. I did it over here. As you can see, it is mentioned as extra step. It is not necessary in your exam. You might do it in your homeworks. If I ask it, you need to do it. You need to do the extra step and checking if your values are right or not. But if I'm not asking, you can do it by your own choice. But if I'm not asking, it is not necessary to do this additional step. As you can see, I did calculate the moments about point B, putting all the values that I calculated as the reactions at point C and A. And at the end, you can see the value that I got is minus 0.11, which is just the error because of the rounding values, almost 0. So my calculation was right. And by following this approach, we could find the reactions in this example over here. Alright. Let's take a look at the next example, which is this beam under these uniform loads, and it also has 5 supports under the beam. Let's see how we can find the reactions in this beam over here. Very similar to what we did in our previous problems. The first thing that we need to do is to find the free body diagram, or draw the FBD or free body diagram. In this specific case, I have to put the forces that we have instead of the reactions. I have a hinge support over here. For this hinge support, we have one reaction in the vertical direction and one reaction in the horizontal direction. I have a roller support over here, and at the end also we have a roller support. For each of these roller supports, we are going to have only one reaction. Also, make sure you include these two hinges in your considerations. So the beam has 4 supports and also 2 hinges in the beam. This is the free body diagram of the beam. As you can see, we had 2 reactions at point A because of this support over here, and we had roller supports at these 3 locations, this point, and this point, and that's why we have one vertical reaction at C, one vertical reaction at D, and also one vertical reaction at F. So this is the free body diagram. We have the loads, and now we can move to the next step, which was finding the situation about determinacy of the structure. We need to see if the structure is determinate or not, and for that, this is the equation that we need to solve. I equal to R minus 3 plus EC. R was the number of reactions. So at point A, I have 2 reactions. At point C, I have 1 reaction, D 1 reaction, and F 1 reaction. These are the list of reactions. And now I can simply calculate R by adding all of these reactions together. So R will be 5. The next parameter or value to find is EC, that is equations of condition. As you know, I have repeated it a lot. Whenever we have a hinge in the structure or in the problem that we are looking at, we have to add EC as 1 or consider one equation of condition. And whenever we have a roller inside the structure or the frame that we are analyzing, we have to consider EC as 2. In this specific case, I have 2 hinges, one at point B, one at point C. So EC for B equal to 1, EC for point E equal to 1, and EC will be 1 plus 1, which is 2. So I have to return the value of EC and R to this equation, and if I do that, the final value will be 0, which means that the structure is stable and determinate. We can use the equations of equilibrium to find the reactions in this structure or in this beam. So we could find the situation about determinacy, and we could see that the structure is determinate. And now I can write the equations of equilibrium and see if I can find the reactions based on these equations. The first equation was summation of forces in the horizontal or x direction equal to 0. This is the free body diagram. The only force that I have in x direction is AX, right? So AX equal to 0. We could simply find the value of one reaction over here. And that is the horizontal direction or horizontal reaction at point A. The next equation is summation of forces in y direction equal to 0. And I have to look at the free body diagram. I have AY, CY, DY, and FY, 4 unknown values. And the other things that I have as the vertical forces are these uniformly distributed loads. So one of them will be 5 multiplied by 40, the other one will be 3 multiplied by 90, and those are calculated over here. AY minus the first uniform distributed load plus reaction at C minus the second uniformly distributed load plus dy and Fy equal to 0. So this is just one equation. I have 4 unknowns and it is not going to help me. I can calculate or include the other equation, which is summation of moments about one point, let's say point A equal to 0. We can calculate the moment because of each of these forces and loads about point A, but I already know that it's not going to help me because we have too many unknowns, and even with 2 equations we cannot find all of them. I did it over here. As you can see, I calculated the moments because of each of those forces about point A, and as you can see I have 1, 2, 3 unknowns in this equation, and considering these 2 equations, summation of forces in vertical direction and summation of moments about point A, these are not going to help me finding the unknown values. What should I do? I have to take advantage of those equations of condition, or in other terms, I have to take advantage of these hinges in the beam. I have one hinge at point B and one hinge at point E. How should I take advantage of these hinges inside the beam? I can break the beam from the place of these hinges and then look at the separated parts of the beam. The most important thing that we have to have in mind when breaking the beam from the place of hinge is that whenever we have a hinge, there is no moment at that location, or in other terms, the hinge only transfers vertical and horizontal force and it does not transfer the bending moment. That's why if I break the beam like this, you can see from point A to point B we have the loading, and at the place of hinge I have only the forces. I don't have any bending moment. If I look at the other segment, the middle segment of the beam from point B to point E, I have the loading, I have the 2 reactions at point C and D. At the place of hinge B and hinge E, I only have 2 vertical and horizontal forces. There is no bending moment. And the same idea for the last segment. The other thing that is very important if we want to solve this problem is that when you are breaking the beam into segments, make sure you put the correct direction of the forces in the hinge. What I mean by that is at point B, I don't have any information about the forces at point B, right? So I can just assume the force at point B in this segment is to the left as the horizontal one and the vertical one is upward. This is just an assumption. You can make another assumption about the directions, but the thing that you have to make sure you do correctly is putting the opposite direction of these forces on the other segment. Or in other terms, it is common to say we have to put the reaction of these forces on the other segment. So if I assume these forces as the leftward and upward, I have to exactly put the reaction of these forces on the other segment. As you can see, this is left, this is to the right. This is up, this is downward. The same idea about point E. It doesn't matter which segment you look at from the beginning or which segment you pick to look at first. The thing that matters is that the direction of these forces on 2 different segments should be exactly in opposite. So for example, at point E, you can see at first I assume this is to the right in the horizontal direction and this is upward in the vertical direction in this rightmost segment. and exactly at point E in the segment next to it, I have the opposite directions of these forces in the other segment. So, two important points. At the place of hinge, only horizontal and vertical forces are being transferred in the beam. There is no bending moment. That was the first point. The second point was that when you are breaking the beam, make sure the forces that you consider on one segment is exactly opposite to the forces that you consider on the other segment. That is the situation that I have for point B in these two segments and also for point E in these two segments. If you follow these two important points about hinges, you can simply take advantage of them in solving the problem and analyzing the beam. So, we could break this beam into three segments: segment AB, segment BE, and segment EF. And now I'm going to look at these segments and write the equations of equilibrium for these segments. At first, I'm going to look at segment AB. Let's take a look at segment AB and see how we can write the equations for this segment. So I have the equations of segment AB, and summation of forces in x direction is equal to 0. This is the segment. I have AX, I have BX, right? And positive is to the right. So summation of forces in x direction equal to 0. AX minus BX is equal to 0. We know that AX is 0 based on the equations that we wrote for the total beam. Let me go back and show it to you. This is over here, right? So AX is already equal to 0, which means that BX is also 0. Now I can say summation of forces in y direction is equal to 0. And that means AY minus 5 multiplied by 20 plus BY is 0, right? AY minus 5 by 20, and this minus is because I assume positive is upward, this uniformly distributed load is downward, so this is negative. I have AY and BY over here, and the third equation that I can write is summation of moments about one point equal to 0. I can say summation of moments about point A equal to 0. If I do that, I can say minus 5 multiplied by 20 and then multiplied by 10. That is the moment because of this distributed load. At first, calculate the total force because of the distributed load. That will be 5 multiplied by 20, area under the load. And then we have to multiply it by the distance from centroid of the load to the point where we are calculating the moment about. Centroid of this load is located at the center of this distributed load, which is 10 meters from the left. And then that is the distance that I have to use in my calculation. 5 by 20, that is the total load, and then multiplied by 10. This is negative because I am assuming positive moment is counterclockwise. This moment is creating, or this load is creating a clockwise moment about point A. Now I have to include the moment because of By. That will be By multiplied by 20. And that is positive because the moment that it creates is counterclockwise. As you can see, it is included over here. And based on this equation, the only unknown is By, and we can simply find By as 50 kN. I can return this value into equation 2 that we have over here. That is done in this line. And I can simply find the value of Ay as 50 kN. The thing that I mentioned over here is that whenever we have a symmetric beam, everything everything will be the same in both sides of the beam. For example, if the beam is completely symmetric and I have one reaction in the left with some value, the reaction at the right will be exactly the same as the one in the left, and the value will be also exactly the same. For example, over here you can see this is completely symmetric. These horizontal forces we said are equal to 0. So A and Y, AY and BY will be equal to each other, and the value should be equal to each other. So we can say these values that we could find over here are correct, and the calculation is right. So I could find the reaction at point A, I could find the vertical force at point B. Now what I can do is to move and look at segment EF, this simple segment over here, and do the same. I can write the equations for equilibrium at this segment, and if I do that, you can see the equations. Summation of forces in x equal to 0, so Ex is 0. As you can see, this is the segment. I hope you can see it properly. So this is the segment. Summation of forces is equal to summation of forces in x direction is equal to 0. So Ex is 0. Then we can say summation of forces in y direction equal to 0. And that would give us Ey plus Fy minus 3 by 20 equal to 0. That is this equation over here. And then the last equation will be summation of moments about a point. We can say summation of moments about point E equal to 0. And since positive is counterclockwise, I have to say minus 3 by 20. That is the total force multiplied by the distance, which is centroid of the distributed load to the point, that is 10. And the other moment will be because of this reaction at point F. So that will be Fy multiplied by 20. That is calculated over here, right? The only unknown in this equation is Fy, and if I calculate that, the value is 30 kilonewton. Now, if I return this value into this equation 2 that we had already, I can find Ey as 30 kilonewton, and these are the two reactions in segment EF. So I could find the reaction at A, I could find the reaction at F, and now there are two unknowns as reactions at point C and D. For finding these, I can follow two approaches, or I can pick from two ways of solving the problem. Looking at the total problem, or the total equations of equilibrium that we wrote at first, or I can look at segment BE. Over here I have the situation of looking at section BE or segment BE, and I'm going to write the same equations of equilibrium. So let's take a look at segment BE and write the equations of equilibrium for forces in x direction. Summation of forces in x direction is equal to 0. So Bx minus Ex is 0. That is the first equation. As you can see, that is over here. Then we have summation of forces in y direction equal to 0. Let me go back and show you the segment. So this is BE. What do we have in y direction? I have this By, which is downward, so I have to put minus By, and then minus 5 multiplied by 20, then plus Cy, then minus 3 multiplied by 70, plus dy, and minus Ey equal to 0. I'm putting the plus or minus based on direction of the forces that I assumed in the free body diagram. And if I got the values as Ey and By negative, I have to include that as the value of the force in my calculations. So this is BE, and these are summation of forces in y direction equal to 0. As you can see, based on these, Based on this equation, I have two unknowns, cy and dy, so it is not going to help me alone. I have to include another equation which is summation of moments about a point equal to 0. Over here, I assumed or I got the point as point B. So I'm going to say summation of moments about point B equal to 0. I think by now you are familiar with the procedure. Just calculating the moments about point B. As always, I'm going to assume positive is counterclockwise. So that will be minus 5 multiplied by 20. That is the total force, and then multiplied by 10, distance from center of the load to the point. Then I'm going to calculate the moment because each of these forces about point B, right? That is pretty straightforward. Cy multiplied by 20, that is positive because the moment is counterclockwise. Dy multiplied by 70 because the moment is counterclockwise. Ey should be negative, so I have to say minus Ey multiplied by 90. That is calculated over here. As you can see, minus Ey multiplied by 90, and the Ey that I got over here, 30 kilonewton, is the value that I have to put over here. Right? This is the equation, and as you can see, in this equation, I also have two unknowns, Cy and dy. So we have two equations and two unknowns. The first equation is summation of forces in the vertical direction equal to 0, and the second equation is summation of moments about point B equal to 0. If I put these two equations next to each other, we can see Cy plus dy is 390. That is this equation over here. And then the second one is this equation, which is this equation over here. So two equations, two unknowns, you can simply put it in your calculator or using the methods that you use from mathematics to solve the system. But once you solve the system, we have Cy as 241 kilonewton and dy as 149 kilonewton. These are the two reactions at point C and D in the beam over here. Cy and dy. Right? So we could simply find the two remaining reactions at point C and D. For the extra step or for checking the validity of the calculations and see if the values are calculated correctly or not, I can return to equation 2, which was summation of forces in vertical direction equal to 0 for the total beam. This equation 2 total, is referring to this equation over here. When I was writing the equations of equilibrium for the total beam, I'm going to just put the values that I calculated from previous steps into this equation and see if the final value is equal to 0 or not. I did it over here, and as you can see, putting the values that we calculated in the earlier steps will give us 0 at the end, which means that our calculation was correct. That was the examples for today. We are going to look at more examples in the next session, but before that, if you have any question and if there is anything that I need to discuss more, don't hesitate to send me an email. We can discuss that, and I'm going to leave the remaining minutes of the class for you to write down these equations and these basically examples and see if you can solve it at home. And if there is anything that I need to discuss more, send me an email or let me know, and we can discuss that through email or WebEx. Thank you very much.